Welcome to the last review video, hopefully. So this is electrochemistry. Electrochemistry is the study of the interchange of chemical and electrical energy. These processes involve the movement of electrons from one species to another, which takes place in redox reactions. This review is going to focus on what redox reactions are, balancing redox reactions, and the parts of an electrochemical cell. Most of this information was covered in honors chemistry. Most of the information that's in this little review is found in Chapter 4 of your textbooks, and a few of the pieces are in Chapter 17. So redox reactions. Redox reactions have two reactions that occur simultaneously called reduction and oxidation. Reduction is defined as a gain of electrons or a reduction of oxidation state. The gain of electrons is always going to cause your charge to go down because electrons are negative. An example of a reduction reaction is shown here. So we have magnesium with a +2 charge gaining 2 electrons, causing its charge to go down by 2 to magnesium 0. Oxidation is defined as a loss of electrons or an increase in oxidation state, so the opposite process. Here, copper metal, which has an oxidation number of 0, is losing 2 electrons to become a copper 2+ ion. These changes in oxidation state caused by a transfer of electrons from one species to another adds another layer to our normal balancing process. So normally we're just concerned that the number of atoms of each element is the same on both sides, but now we need to worry about whether the electrons lost and gained are equal as well. So some terms, rules, tricks that you need to know. First is a half reaction. So since reduction and oxidation reactions must occur together, but they're each kind of separate, both of those things are called half reactions. So we have an oxidation half reaction and a reduction half reaction, which make up each part of the redox reaction. Species. Since we're dealing with both ions and elements, things that are charged and things that are not charged, we need a generic term that will apply to both, and species is the winner. Oxidation number. So oxidation number is more generically known as the charge, but since covalent things aren't really charged, they're referred to an oxidation number. The rules for assigning oxidation numbers are coming up. So the oxidation state of an element is always 0, including all elemental forms of the element. So anything that's diatomic or anything that has multiple atoms of the same element in one thing also has a charge of 0. So ozone would be 0, S8 would be 0. The oxidation state of a monatomic ion is the same as the charge. So if you have copper +2, the charge is +2. In compounds, fluorine is always assigned an oxidation state of -1 because it is the most electronegative element, so it will always take the electron. Oxygen is usually assigned an oxidation state of -2 in its covalent compounds, also in its ionic compounds. The only time that oxygen isn't the most electronegative element is when it is bonded to fluorine, so that's one of the exceptions for it. The other exception is when oxygen is in a peroxide or polyatomic ion, where each oxygen is assigned an oxidation state of -1. And again, when oxygen is bonded to fluorine, since fluorine has a greater electronegativity, it takes the electron away from oxygen, forcing oxygen to take a positive charge. Hydrogen is assigned an oxidation state of +1. Metal hydrides are the exception to that. There, since metals become positive because they lose their electrons, hydrogen takes a -1 charge. The sum of the oxidation states in a compound must be 0, and the sum of the oxidation states in a polyatomic ion must equal the charge on that ion. The other trick is this Leo says GER, which stands for lose electrons oxidation and gain electrons reduction. Assigning oxidation numbers. So here we have some practice for that. So first one we have is HNO3. So in general, you want to assign oxidation numbers to the things that you either have rules about or that only really have one normal oxidation number. Here we have a rule about oxygen, which is -2, and a rule about hydrogen, which is +1. Since each oxygen is -2 and there are 3 of them, that leads to a -6 charge. The hydrogen again is a +1, which leaves me with +5 to take care of, which means my N equals +5. Next we have CuSO4. Copper has multiple charges, as does the sulfur. Oxygen is -2. Here, SO4 is a polyatomic ion, which itself has a -2 charge, which means that copper must be taking its +2 charge. Sulfur, on the other hand, is still a bit of a gamble. So, we know that oxygen is -2. We can figure out copper is +2 from the charge of the sulfate, but we still need the charge on the sulfur. Since O is -2 and there are 4 of them, that leaves me with -8. Copper is giving +2, which means my S must be +6. MgC2O4. Again, Mg is +2. It's group 2 metal. There is no other charge for it. Oxygen's -2. Here, when you do your math, your carbon ends up being +3, which is not a normal charge for carbon, but it is possible in this particular polyatomic ion that carbon is doing that. So even if your charge doesn't make sense, it's probably like if you've done your math. So go back, double check, but if that's what you get, that's what you get. N2, since it's an element by itself, is going to have a charge of 0. Al2CO33. Al is +3, O is -2. That leaves me with my carbon to figure out. So I have a +6 for my aluminum, a -18 for my oxygen, and so my carbon ends up being +4 there. SO3 2-. Since this is a polyatomic ion, my charge of the overall thing needs to equal -2. O is -2 itself, so it's with a -6, so my sulfur must be +4. So how do you know if a reaction is a redox reaction? The most important thing is you need to have a change in the oxidation state. If there is no change in oxidation state, then no electrons have been lost or gained, so it cannot be a redox reaction. So when you're asked to figure out if a reaction is redox or not, the first thing you should do is assign oxidation states. If there's no change, then it's not a redox reaction. If there is a change, then it is a redox reaction. So here, anything by itself is 0, so Mg is 0, O2 is 0. When you're in a compound, you must have charges, so +2 -2, so that one is a redox reaction. Second one, NO2 goes to N2 plus O2. Again, things by themselves are 0. Things in compounds must have charges, so again, this would be a redox reaction. Here, again, anything by itself is 0. Anything in a compound must have a charge, so this would be a redox reaction. And here, if you go through and assign all those, if you look carefully, nothing has changed. So, as a general rule, single replacement reactions must always be redox reactions because you always have an element going into a compound. Synthesis and decomposition tend to be redox reactions, but you have to be sure that you have some elements in there. If you have compounds going to compounds, you may or may not have an actual change in oxidation state. But as a general rule, synthesis, decomposition, single replacement are usually redox. Double replacement tend not to be, although they can be depending on what's going on. So identifying oxidation and reduction in the easy problems. Your steps. First, you need to assign your oxidation numbers. Second, determine what has changed its oxidation number and connect the species. Third, write out the two half reactions. Fourth, balance each half reaction with an appropriate number of electrons to make the charge of the reactants equal to the charge of the products. And then add coefficients to make the number of electrons lost equal to the number of electrons gained. Put those changes back into the original equation, and then make sure that the rest of the elements are balanced as well. So here's our example. First step is to assign oxidation numbers. Copper is +2, O is -2, N must be +5. Al is 0 since by itself. Al is +3, O -2, so N must be +5. Copper is 0. Okay, so what's changed? Copper's changed, aluminum's changed. So draw your connecting arrows to those things. Then you're going to pull those things out of that equation. You'll see that the N and O haven't changed, so those are called the spectators in this reaction because they don't really do anything, they don't change. So here we're going to pull these out. Right, so aluminum is going from 0 to +3, which is going to be oxidized, and the copper is going from +2 to 0, which means it's being reduced. So now I need to put the electrons in to fix those. So the 3 electrons are going to need to go onto the product side, and then for the copper, the electrons will have to go onto the reactant side. So which is oxidation, which is reduction? So if you look at the change in charge, copper is going down, which indicates it's gaining 2 electrons, and aluminum is going up, which indicates it is losing electrons. So since the copper is gaining 2 electrons and the aluminum is losing 3 electrons, you can't have them losing and gaining different amounts of electrons, so you have to fix that. To fix that, you add coefficients to the half reactions to make the number of electrons lost and gained equal. So you're going to multiply the aluminum reaction by 2 and the copper reaction by 3. And then you put those changes back into the original equation. The last thing you need to do is make sure that all the spectators are balanced as well. So make sure your nitrogens and oxygens work out. If you look at your copper to nitrate, you have a total of 6 nitrogens. Same thing on the product side, and you have a total of 18 oxygens and 18 oxygens. Right, reducing agent and oxidizing agent. The agents are the species that cause that reaction to happen. In other words, the reducing agent is causing something else to be reduced. This happens because the reducing agent is giving off electrons that something else must take in, therefore being reduced. The reducing agent is giving off or losing electrons, which means it's undergoing oxidation. So in summary, the agents are undergoing the opposite process. So in the reaction we just looked at, the copper 2+ is being reduced, so meaning it's gaining electrons. So it is the oxidizing agent. The Al0 is the reducing agent because it's being oxidized. So the Al0 is giving off its electrons and the copper 2+ is taking them. So they're kind of causing each other to lose and gain electrons. Balancing with the half reaction method. So this method needs to be used when there are some covalent bonds involved in the species that are being oxidized and reduced. So in the previous example we had ionic compounds, and those, as you know, will actually split apart. So you can pull the metals out separately and look at their loss or gain as individual species. But when things are covalently bonded, you can't really pull them apart from each other because they're physically bonded together. So you need a different method. These reactions are done in either acidic or basic solution. I'm going to go through the rules on how to do this here, but we're going to go over this in class. So I don't expect you to figure this all out through this video. We are going to learn this in class as well. So I'm going to go through the acidic method first, since it's more common. The basic method pretty much uses the acidic method plus a couple extra steps. So the steps for the acidic method. First, you need to write the reaction in ionic form, if it's not already. You need to assign oxidation numbers to identify what is being oxidized and what is being reduced. You need to write the separate half reactions for oxidation and reduction. So far this is very similar to what we've done before. But here you need to keep the formula of the species being oxidized or reduced together. Meaning if it's covalent, like NO3 negative, the nitrate ion is a covalently bonded thing, you can't pull the N out separately. You have to leave it in the nitrate ion. For each half reaction, you balance all the elements except for hydrogen and oxygen. So make sure all of the things that are oxidized or reduced are balanced. Then you balance your oxygen using water, and you balance your hydrogen using H+. Since it's an acidic solution, you should have plenty of those floating around. And then you balance the charge using electrons. Then everything else is pretty much the same. You multiply each half reaction by a coefficient to make the number of electrons lost and gained equal. You recombine the half reactions and cancel or reduce any identical species present as reactants and products. That usually means H+ or water. And then you check that all the other elements, all the spectators and charges are still balanced. Next thing we have a little flow chart. This is also on your textbook, I believe. So it just kind of goes through those steps. So you'll see they have right separate half reaction, and then your balancing order is elements except hydrogen and oxygen, then oxygen using water, then hydrogen using H+, and then charge using electrons. The next page we have our basic one. So again, the beginning is pretty much the same. So you write out your half reactions, you do the elements except H and O, you use water to balance oxygen, you use hydrogen to balance H+, and you do your charge using electrons. Now this is where it gets different. Once those two things have come back together, You add your half reactions, you cancel the identical species, check that the elements and charges are balanced. Now here you'll see in the blue, it says you add hydroxide to both sides of the equation equal to your H+. This is how it becomes in basic solution. The hydroxide plus hydrogen will make water, and then you'll be able to cancel out any extra waters, which will hopefully leave some hydroxides behind and allow you to have it in basic solution. Then the end step is the same. You check that elements and the charges are balanced. So we're going to do these equations in class, but I wanted you to have some idea of what was going on before we tried to do them. All right, the last thing in this review is about electrochemical cells. So there are two types of electrochemical cells, galvanic and electrolytic. Galvanic cells are spontaneous, meaning they convert chemical energy into electrical energy, and electrolytic cells require electrical energy to allow the chemical reaction to occur. Both of these are made up of the same parts. The parts to an electrochemical cell include an anode, which is the electrode where oxidation takes place, a cathode, which is the electrode where reduction takes place. Electrodes are just pieces of metal, and they can either be the thing that's directly undergoing the oxidation or reduction, or they can be someplace for those reactions to occur on that allow the transfer of electrons. A salt bridge, which is a tube or other piece that allows the flow of ions between the two half reactions, and a wire which connects the two electrodes and allows the flow of electrons. A couple of rules about electrochemical cells. The electrons are always flowing from anode to cathode, from where they are lost to where they are gained, because the anode is where oxidation occurs. Electrolytic cells must also have a power source hooked up in their system to allow that reaction to actually happen. Red cat gets fat, meaning the reduction is occurring at the cathode, which means you're always going to be gaining metal on the cathode, so it will always be getting larger. And voltage for galvanic cells is always positive, and voltage for electrolytic cells is always negative. So here we have a picture of a galvanic cell and an electrolytic cell involving the same two reactions with cadmium and copper. So what's the same and what's different? So first you'll see at the anode in both of these, oxidation is occurring. You're losing electrons. At the cathode, reduction is occurring in both. The electrons are flowing from anode to cathode in both of these things. Things that are different. You'll notice in the galvanic cell that voltage is being produced. So you're measuring it with a voltmeter. In the electrolytic cell, voltage is being supplied through the power source. You'll also notice that the charges assigned to the anode and cathode are opposite. So the charge assigned to the anode in the galvanic cell is negative, and the charge assigned to the cathode is positive. Now, if you think about the way the electrons are flowing in the galvanic cell, that makes sense. They should be going away from the negative and towards the positive spontaneously. In the electrolytic cell, the charges assigned are opposite. So the electrons are moving away from the anode, which is assigned a positive charge, and towards the cathode, which is assigned a negative charge, which should not be occurring spontaneously, which is why it requires voltage. The other thing that is different is you'll see that the more active metal, which in this case is the cadmium, is the one that's doing the oxidation in the spontaneous or galvanic cell. That's because it wants to lose the electrons more than the copper does. You'll see that they're switched in the electrolytic cell, which again makes sense, because it should be occurring spontaneously in galvanic or doing what it wants to do, and being forced to do what it doesn't want to do in the electrolytic cell. Right, so how do we know whether to make the metal the anode or the cathode? So we use an activity series, which is basically a list of the metals in order of their reactivity. Metals that are active or reactive tend to lose electrons, thus they want to be oxidized. So if you want to have a galvanic cell, you should have the more active metal be the anode and the less active metal be the cathode. The opposite is true for an electrolytic cell, so the more active metal becomes the cathode. So on the website there should be a book assignment for part 1, I believe. You're probably going to have a quiz on this information in class after we do a review worksheet. And that's it. Hope you enjoyed review for electrochemistry.